In this video we're going to look at excavations. Excavations have much the same problem as retaining walls in that when you're excavating you've got to keep a stable slope to be able to do the excavation safely. So some of your options might be to bench it back or to slope it, but oftentimes you don't have that sort of space available to you, so you have to work with vertical slopes. So you've got to figure out some way of shoring the slope, the soil as you go down. Another issue you have is you're trying to excavate and you're trying to support the excavation at the same time, which means that you have to come up with some ways of being able to stabilize your work area as you go. In the previous video we talked about sheet piles, we talked about secant piles, we talked about diaphragm walls. They are all ways of keeping a stable vertical slope as you go down. In fact, all three of those involve building the stable vertical wall before you actually start the excavation. And then there are other ones like this post and panel, where you put the posts down and you install the panels as you go down. You can see this one as well, as they went down they also were installing anchoring to provide intermediate anchoring, so that it's not just the cantilever action of the post that's supporting the wall, it's also the tie back as well. So they would have installed those temporary tie backs when they got down to a certain level. So in this video we're going to look at another issue you've got with excavations. Obviously retaining the walls is one issue, but the other one is water. When you go to deep excavations, you're usually below the water table, and sometimes you're working right next to water bodies such as the sea or rivers or canals. So how do you keep your site dry and enable you to do the work? One way of doing that is to dewater it using a sump. So you can see here they're doing an excavation and they've got a collector drain and a sump. So they've dug in a hole at the end. So here you can see there's a hole at the end, and in that there's a pump. So the water that flows into the excavation is collected, flows to the sump, and it's pumped out by the pump. Now this works for shallow excavations when there's not all that much water coming in, but if there is a lot of water, if you're down below the water table quite a bit, this is not going to work, because the water coming in is just going to flood the works, and you're not going to be able to pump it out fast enough. It will also destabilize the sides of the slope as well. So it's good for low water flows, but if you've got high flows going in, it's not such a good option. For the higher flows, or where you're going deeper, the well point system is a good way to go. So you can see that what it's got there is a whole lot of little wells around the edge. Each one of those has a wand going down below the water table and is an inlet, so it's got a perforated pipe. All of those wands are connected to a manifold, which is connected to a pump. So the pump pumps and draws the water from the wands, each one of them, and then pumps them out to a discharge point. By doing this, it lowers the water table, because all of them are all pumping together, and takes that water table down below your excavation. You can have multiple stage well pointing systems, so you can get down quite deep. I've seen them down to about 10 meters by using multi-stage well point systems. If it is a cohesive soil, you may not have to have wells at such close proximity. You can just have wells that maybe every 5-6 meters or something like that. So it all depends on the type of soil. So you can see there's a well point system here, there's the manifold, there's the pump, and those guys are sort of working in the dry even though they're below the water table. Another issue you might have if you're working close to the sea or close to a river or something like that, is that there is no soil between you and the water. So that's what a cofferdam is, and you can see here they've got a sheet pile cofferdam. It's all supported with these beams here, this ring beam here, supporting it all against the hydrostatic pressure. So there's a ring beam high and low, and it's basically providing a barrier between the water and the station. Coupled with this needs to be a pretty significant pumping system to pump the water out, because there will be leakage going in and underneath the sheet piles. So the sheet piles would have to be founded quite deeply into an impermeable soil preferably, and also the pumping system would have to be quite substantial. Another variation is where you're actually well below the water table, and you need a watertight structure to allow the installation of a foundation. So for bridge foundations, for example, normally bridges are built in the water. Caissons are quite popular for that. For large piles, caissons are also used. So the difference between a board caisson and a board pile and a caisson can be quite vague sometimes. So basically the caisson chamber becomes part of the foundation. You can have three different types: box, open and compressed air, and we'll look at each one of those in turn. So a box caisson is basically that, just a box. So you can see here they've got a bridge foundation or foundation for something, and it is filled with air at present, so it is taken to where it's supposed to go. They use dredgers to shape the bottom, and then they will sink this. They'll fill it up with water and sink it down onto where it's supposed to go. Once they've got it in the right location, you can use pump air in or remove air to give it a bit of buoyancy and lift it down or whatever. Once you've got it in the right place, then you pump concrete in, so it is now permanently negative buoyancy. It's going to stay in place. So that's a box caisson. Another one is an open caisson. So in this case there is no bottom to it. It will sink if you put it in the water. So what you do is you oftentimes you see these on the ground, and they'll start excavating, and as they excavate, they will excavate underneath the box, and the box will start sinking down under its own weight. You can also, if you've got a structure above it, you can jack it down off that structure. So it's suitable for soft clays where you've got an impermeable soil around it, so you're basically just digging out as you go. A variation on the open caisson is the compressed air caisson, which allows you to put air pressure in and keep the water out as you're going through. So in this case here you have a closed caisson and a workspace there. The water is going to want to go underneath the caisson and up into the workspace. So what you do is you pressurize the workspace to the same pressure as the water. So the water can't come into the workspace because the workspace is at the same pressure as the water. That means that you are working in a compressed air atmosphere. There are risks associated with that, the same risks that divers have, the bends. So if a person is in the workspace and then they go straight out to atmospheric pressure, the nitrogen in their blood will actually start boiling, and they can get the bends, which is really quite painful and can actually kill you. So in association with a compressed air caisson, you need a decompression chamber, so workers will go into the caisson work for a 4 to 8 hour shift, and then they'll have to spend a couple of hours decompressing before they can actually go back out into the normal atmosphere. So this is quite popular for bridges. It's one of the oldest ways of building bridge piers. The Brooklyn Bridge, which was built 150 years ago, used this method. The Auckland Harbour Bridge also used this method. So these piers here were actually built using compressed air caissons. So there's some guys sort of working in there. You can see that's the top of the caisson, and that is the seabed. So these guys are working in the seabed. When they came out, they hopped into this decompression chamber, which allowed them to decompress and then sort of leave. So they used to have to spend a couple of hours at the end of each day in the decompression chamber.